In our discussion of kinetics, we've been talking about rate laws. We said that the rate law was going to be an equation that relates our rate to the concentration of our reactants. Now, those rate laws are going to be determined by experiment. And the form of the rate law depends on the reactants and how they interact with one another. This interaction is based on the reaction mechanism, which we'll discuss later in our chapter. The reaction mechanism cannot be determined from the balanced chemical equation. As a result, the rate law cannot be determined from the balanced chemical equation. They must instead be determined by experiment. All reaction rate laws must be determined by experiment, and there are two primary methods that we can use to do so. We have what's called the initial rate method, and we have a graphical method. With our initial rate method, this requires a series of several experiments. In these experiments, we must know initial rates for varying initial concentrations of reactants. So remember our initial rates. We get these from those graphs of concentration versus time. They would be that slope of the tangent line at a time of 0. So we would have different experiments in which we change the initial concentrations and we identify that initial rate. What we would then do is compare initial rates for two different experiments in which one reactant is held constant while the other one changes. This allows us to see how the rate depends specifically on the reactant whose concentration was changed. So if we think back to our common orders, remember that first order means that rate is directly proportional to concentration. In a first order reaction, if the concentration difference between the two experiments were doubled, we would see that the rate would double. Using this, if the two experiments involved doubling the concentration, and as a result we saw that the rate doubled, we would know that the reactant is first order. Same concept applies to a reaction that is second order. In a second order reaction, doubling the concentration leads to the rate being quadrupled. So if we saw this in our experiments, we would know the reactant was second order. So we've got that other order, we've got 0 order, and we're asked what would we see if the reaction was 0 order. So we've got to remember that 0 order means that the rate is independent of the reaction concentration. So that means no matter what I do to the concentration, the rate does not change. So if we change concentration and we saw no rate change, then we would know our reaction was 0 order. 0 first and second order may often be easily recognized just by looking at the data. However, other orders are not as obvious, and sometimes our common orders may not be as obvious either. In either of those cases, we can solve for our orders mathematically. So with our problem here, this is problem number 5. This is going to walk through the steps of how we would determine the order or the rate law for a reaction. So we've got the following reaction. We've got nitrogen monoxide reacting with hydrogen. We're producing N2O2 and water. And then we're given a series of 3 experiments. And we've got concentration information and we have initial rate information. From this data, we can determine our reaction orders. So we would start, as with our previous examples, we start with our general form, which would be that my rate equals the concentration of my first reactant raised to some power times my second reactant raised to some power. And what we're trying to find here using this data are those powers, those M and N values, our orders. Now in determining M, the effect, and so M is the effect that the nitrogen monoxide has on the rate. We would need to choose 2 experiments in which NO changes, but hydrogen remains the same. So here we're specifically told to compare experiments 1 and 2. So as we compare experiments 1 and 2, the NO changes, but the hydrogen stays the same. So if we compare those two experiments and we're looking at the nitrogen monoxide concentration, we're asked by what factor has the concentration increased. We're just saying how has it increased. Now these numbers are pretty easy to look at. We can tell from experiment 1 to experiment 2 that the concentration doubled. So 2 is the factor the concentration has increased by. It has doubled. If we can't see that, what we would do is we would take experiment 2, divide it by experiment 1. And we're going to get 2. So that 0.3 is 2 times larger than the 0.15. So that tells us that this reaction would be second order with respect to that nitrogen monoxide. Or sorry, we haven't got there yet. We've just doubled our concentration. Now what we've got to do is see how the rate changed. And so here our numbers are a little bit more complicated. It's not as obvious to look at and tell how the rate changed. So we're going to take experiment 2 divided by experiment 1. So 3.42 times 10 to the negative 5th divided by 8.54 times 10 to the negative 6th. And the value we get is 4. So that means that my rate is 4 times faster. Now from that, again, we may be able to judge and see what our order should be if we recognize that 2 squared equals 4. But if we don't recognize that, again, we're going to solve using our logs. So what we're going to do is we're going to take the factor by which my concentration changed. So my concentration doubled. We raise it to m. We set it equal to the rate change. The rate change was 4. Again, our m will be 2, but if we don't see that, we're going to take the log of both sides. So log of 2 to the m equals the log of 4. We rearrange. So my m is the log of 4 divided by the log of 2, which gives me 2. So now we have the order on our nitrogen monoxide. The nitrogen monoxide is second order. So next we need to determine the order on our hydrogen. We're going to repeat the same process. We're looking at the effect that hydrogen has on the rate. So we're going to look at 2 experiments in which we change hydrogen's concentration, but NO stays the same. Now, when we're picking these experiments to compare, they're not necessarily consecutive experiments. We're just looking at the numbers and how they changed. Here, we're going to have to compare experiment 1 and 3. Because from 1 to 3, NO stays the same, which is what we want, but my hydrogen changes. If I compare 2 and 3, that's not going to work because both the NO and the H2 change. We want reactions in which, or experiments in which only one reactant is changing. So if we compare experiment 1 to 3, we go from 0.15 to 0.45. Our concentration has tripled. Again, if we don't see that, we're just going to divide. We do 0.45 divided by 0.15, which would be 3. So we have tripled our concentration. So looking at our rates, we want to know how our rate changed. So we're taking experiment 3, dividing it by experiment 1, and we're going to end up getting a factor of 3. So just like we did before, we're using this to determine our n value. So we're taking the factor by which, or the amount by which my concentration changed, which was tripling. We raise it to our n, and we set it equal to the rate change, and the rate change was 3. So here, my n would be 1. Again, if we didn't recognize that, we're going to take the log of both sides, we're going to rearrange, and we're going to solve for that n. So combining these, we can determine our rate law. our rate equals K times the concentration of NO squared times the concentration of H2. Now notice here that I did not write the 1. We said that the N value is 1, but I have not written the 1 here. We omit that 1. That 1 is understood to be there. We showed it previously just to show some examples, but typically we're going to leave that 1 off in our rate law. Now, once we have our rate law, we can use our experimental data to determine our K value. We could pick any of our experiments, it doesn't matter. We're going to plug that experimental data into the rate law and we're going to solve for K. Here we're just going to pick experiment 1. So experiment 1, the rate was 8.54 times 10 to the 6th molarity per second. That is going to equal K times NO's concentration of 0.15, and that value is squared, times hydrogen's concentration of 0.15. Doing some simplifying, 0.15 squared times 0.15 is going to be 0.15 cubed. My units will be molarity squared times molarity, which will be molarity cubed. And then rearranging to solve for our K, we're taking our 8.54 times 10 to the negative 6th. We're dividing it by 0.15 cubed, molarity cubed. And so we will end up with a K value of 2.53 times 10 to the negative 3rd. And our units, remember, we've got to track those units because the units change. Molarity on top cancels. One of these molarities on the bottom cancel. And I end up with 1 over molarity squared times seconds. Now, on our worksheet, we had some additional problems. We've got problems 6 through 9. 6 through 9 give you guys some additional practice with determining the rate law, just like we did with problem number 5 here. So I would encourage you guys to spend some time on your own, work through those problems. I will post an answer key in order for you to check your work.